Hey everybody, my name's John Broadwell. I'm the creator of the open source Serial Wombat project and embedded systems consultant for hire at my company, Broadwell Consulting Incorporated. You need help, give me a call with something. Today we're going to take a video where we're going to look at taking analog digital conversions that range from 0 to 5 volts in a 3.3 volt system. And there's a couple of ways that you can do that. One is the classic resistor divider method, which has some advantages. It's cheap, it's easy, and some disadvantages. You inherit the accuracy problems from the resistors that you pick. It has a constant current drain, and it adds impedance to your circuit, which is not awesome. So the other alternative is to use a chip that directly measures 0 to 5 volts, and it just so happens that the Serial Wombat 8B chip goes from 0 to 5 volts. It's available right now as part of a Kickstarter campaign through April of 2025 and will be available later this year on Amazon. It's essentially a CH32V003 microcontroller with my custom firmware running in it, which turns it into an I2C controlled device. The Serial Wombat 8B can take an input voltage from 3 to 5 volts, and so it can measure any voltage up to its input voltage. And it's possible if you have a 3.3 volt device, like say an ESP32, ESP8266, Raspberry Pi Pico, SAMD21 based SHAO or whatever, that those are all 3.3 volt devices. But you can go ahead and put a 5 volt device on the bus if you keep your I2C at 3.3 volt pull-ups. So a few things to know about mixing 3.3 volt and 5 volt I2C devices. Number one, you have to use the pull-ups. Trying to get by on the internals inside of the microcontroller is not a good idea because that 5 volt, you're already only giving it a part of what it expects on the voltage transitions on the clock and data. So you need those stronger external pull-ups. Number two, one of the things that's great about the Serial Wombat 8B board is that it has solder jumpers to enable onboard 2200 ohm pull-ups. Don't use that if the chip is going to be powered at 5 volts, but the rest of your system is 3.3, because then you'll be feeding 5 volts in the I2C bus. It might work okay, it might not, or it might kill the other chips over time. So don't do that. Use external discrete pull-ups instead. And finally, you may have to slow down your I2C bus or vary the pull-up resistance. Again, we're taking transitions that are not going as high or as fast as they would on the 5 volts. And so you're not going quite as far above the low to high threshold on the chip that's running at 5 volts. And so you'll want to take a look at that. One of the things you might do is put an analog oscilloscope on your clock or data lines and see what they're actually doing. Are you getting nice smooth transitions or do they look softer than what you'd like, in which case you may need to vary the pull-ups or you may have to slow down your I2C bus. So let's take a look at our sample circuit real quick. Here we have an ESP8266 based node MCU. I picked this board because it runs at 3.3 volts, and the ESP8266's ADC internal is one channel and it is notoriously horrible. So it's a great candidate to add an external I2C based A to D converter. And what we're going to do here is we're going to hook up the Serial Wombat chip. This particular chip is at address 0x60. It does not have the solder jumper enabled. I enabled the power LED so that we can see the thing working. And we have a build that's been downloaded into it that includes analog to digital conversion. Virtually all the available images for it do have that pin mode enabled, so we don't have to do anything there. Okay, so let's take a look at the Arduino sketch. We're going to include serialwombat.h. This assumes you've already installed the Serial Wombat Arduino library. We're going to instantiate a Serial Wombat chip. We're going to instantiate a Serial Wombat analog input. We're using the 18AB extended ones. Even though this is an 8B, those are compatible with the 18AB extensions. We'll put it on pin number 3, so we'll call it analog in 3. In setup, we're going to call wire begin, serial begin, and then Serial Wombat begin. We'll have it just find it on the bus. It's the only one that's out there. And then we'll call analog in 3 begin on Serial Wombat pin number 3. And then in our loop, we're just going to read analog in 3 and we're going to have the Serial Wombat chip converted to millivolts based on its own measurement of the VDD, which will be somewhere around 5 volts coming in from the USB power supply from the Node MCU board that we're using. And again, the Node MCU is providing a direct 5 volts to the serial Wombat chip, but it's using the Node MCU's 3.3 through 2200 ohm pull-up resistor to provide 3.3 volts on the I2C Bus. If we go to the serial monitor, we see we're getting random results. That's because it's not connected to anything. So I've got just a 3 AA battery box here so that we can get something around 1.5, 3, or 4.5 volts. So I'll connect up the first one. This is to pin 3. And we can see that we get 1.57 volts. If we do 2 batteries, 3.1. And if we do all 3 batteries, we get 4.7 volts. So, we can see clearly we've got our 3.3 volt system over here. We're using a 3.3 volt I2C bus and able to make 5 volt measurements through the serial Wombat chip without use of a resistor divider or any other kind of specialty circuitry. So that's all for today. If this is useful to you, hop on over to the Kickstarter here in April and get a handful of these chips. They're designed to be really, really inexpensive. Less than $1.50 each is my goal. And until we speak again, have fun and keep making stuff.